welcome back to Sustainability and Engineering. I am Engineer Shahzad Syed, Senior Mechanical Engineer and your host for the session. In our previous session, we spoke about the bigger picture of sustainability and engineering. Why engineering today is no longer just about designing systems, but about delivering safe, efficient, compliant and future-ready buildings. We discussed how engineering decisions impact operational efficiency, life safety, long-term performance, and ultimately the people who use the buildings every day. Today's session builds directly on that foundation. This marks the formal beginning of our CPD series, where we move from why of the engineering into how of the real projects. Today's CPD is not about formulas, software, or calculations. It's about something far more important. Why some projects run smoothly and why others turn into stressful disputes. Every one of us has seen it. A project starts well, drawings are approved, construction begins, and suddenly, scope argument starts, variation increases, claim appears, relationship become tense. Most people think that this is because of bad engineering or bad intentions. In reality, it usually happens because the project type and the MEP scope were not properly understood from the beginning. So today's topic is understanding project types, MEP scope gaps, variations, claims and dispute. This session is not only for MEP engineers, it is equally important for project managers, quantity surveyors, design managers, developers and even non-technical stakeholders. Because scope problems don't belong to one discipline, they affect everyone involved in the project. What I'll be sharing today is based on real projects, real disputes and real lessons learned, not textbook theory. So before we go deeper, let me first show you how and what we will cover in this session and what you will take away from it. Before we go deeper, let me clearly set the direction for this CPD session. By the end of this session, you should be able to look at any project and confidently answer very few important questions. Firstly, you'll be able to identify what type of project this actually is, not just architecturally, but from an MEP risk point of view. Because once you understand the project type, you automatically understand the level of complexity, authority involvement, and risks. Secondly, you'll clearly understand what MEP scope really means, not just drawings, but the full end-to-end responsibility from concept to approvals to handover. Third, we'll break down where scope gaps come from. You'll start recognizing them early, instead of discovering them during the construction when it is already too late. We'll then look at how variations are actually created and approved in real projects. Not in theory, but the way that they happen between engineers, QS, project managers, and clients. You'll also clearly understand the difference between a claim and a dispute, and why not every claim needs to turn into a fight. We'll touch on FIDIC in simple terms, not legal language, but how it practically allocates risk between the employer, the contractor, and the engineer. Because we are working in UAE, we will also discuss how authorities trigger late changes and why authority requirements often override assumptions made at the tender stage. And finally, I'll share what a senior engineer or engineers do differently, how they think ahead, manage risk early, and protect both the project and their own professional responsibility. If you take these points away from today's session, you'll find that projects become smoother, discussions become clearer, and your professional protection becomes much stronger. With that roadmap in mind, let's start by going back to basics and understanding what a project really is from an MEP perspective. Let's pause for a moment and do a quick reality check. Think about projects you have worked on, site, design offices, or meetings. How many times have you heard the statements like this? This is not in our scope, this was included in the tender. This was contractor responsibility, this is consultant responsibility. Almost everyone in this room has heard or said at least one of these. And here's the important thing. These arguments don't usually happen because people are bad engineers, bad contractors, or bad consultants. They happen because the project type and the MEP scope are not clearly understood or aligned at the beginning. When scope is unclear, decisions become messy, coordinations break down, approvals get delayed, variation increases, claims start appearing, and relationships slowly deteriorate. But when the scope is understood properly from the start, design becomes cleaner and more focused, coordination becomes logical and non-reactive, authority approvals become smoother, variations reduce significantly, claims are easier to manage or avoid altogether, and most importantly, professional relationships improve. So today, we are not just learning engineering concepts or contract terms. We are learning how to protect ourselves professionally, how to reduce unnecessary conflict, and how to contribute to projects that actually run the way they are supposed to. With that in mind, let's step back and clearly understand what project really is from an MEP point of view. Let's now go back to absolute basics. In simple terms, a project is often defined as a temporary effort to create a unique building or facility. That definition is correct, but for us as MEP professionals, it is incomplete. From an MEP perspective, a project is not concrete blocks, finishes, or elevations. Those are important too, but they are not what makes a building work. A project from MEP point of view is a living system. It must keep people comfortable through the air conditioning, provide reliable power, supply clean water, protect life through fire life safety systems, maintain health through proper ventilation systems, operate efficiently through sustainable design. If any one of these systems fails, the building may exist physically, but it will not function properly. Now here is an important point. A villa, a hospital, and a data center may look similarly structured. They have all slabs, walls, and finishes. But MEP-wise, they are completely different worlds. They have different loads, they have different redundancy requirements, they have different authority involvement, they have different risk levels, and they have different consequences of failure. And these leads to key lessons. If you misunderstand the function of the building, your MEP design will be wrong, even if your calculations are perfectly correct. So before we walk and talk about scope, variations, and contracts, we first need to understand what type of projects we are actually dealing with. Now that we have understood what a project really is from a MEP point of view, let's classify project types the right way, not architecturally, but based on MEP complexities and risks. This is important because project type automatically dictates how you design, how you coordinate, and how much risk you are carrying. Let's start with the simplest category, residential projects. Now, residential projects are primarily comfort-driven and cost-sensitive projects. Typical characteristics are relatively low loads, simple systems, and minimal redundancy. If the air conditioning fails, it causes discomfort, but it doesn't cause a disaster. If power fails, people will wait. Life continues. Because of this, residential projects demand simplicity and cost control, not over-engineering. Now let's go to commercial projects. Commercial projects are a step higher in complexity. Here you start dealing with higher HVAC loads, mandatory fresh air and ventilation requirements, emergency lighting and fire life safety systems. Authorities become much more involved at this stage, and compliances become more critical. Failure here may not be life-threatening, but it can cause business disruption, financial losses, and reputational damages. Now let's go to institutional projects, such as hospitals, schools, mosques. This is where MEP becomes life-critical. In these institutional projects, life safety is the priority. Redundancy becomes essential. Inspections are strict and very frequent. Hospitals require zoning and filtration. Mosques experience extreme peak loads during prayer times. Schools demand good indoor air quality for health and comfort of the students. In these buildings, MEP failure can directly affect human life. Now let's go to industrial and specialized projects such as factories, data centers, plants, etc. This is a completely different category. Here, MEP is not a supporting service. MEP is the project itself. HVAC protects machines, not people. Electrical systems dominate the design. Redundancy is compulsory in these kind of projects. Downtime directly equals money lost. A few minutes of failure can mean massive financial impact. So when you look at the project, the first question should always be, what type of project is this from an MEP risk perspective? Because project type immediately tells you, first, the level of complexity, second, the degree of authority involvement, third, the redundancy required, and fourth, the overall risk exposure. And once you understand that, you are ready to clearly define MEP scope, which is what we will look at next. This is where a very common misunderstanding needs to be corrected. Many engineers think that MEP scope means drawings. That is one of the biggest mistakes we make in the projects. Drawings are important, but they are only one output of MEP scope, not the scope itself. In reality, MEP scope is end-to-end responsibility. It starts long before the first drawing is issued, and it continues long after the construction is completed. MEP scope includes defining the concept and design intent, carrying out load calculations, selecting the right systems and equipment, ensuring authority compliances, managing coordination with other disciplines, providing construction supervision, witnessing and validating testing and commissioning, and finally, ensuring proper handover and O&M documentation. All of this together is MEP scope, not just lines on drawing. Now let's look at how this plays out across the project stages. Design stage. The design stage is where around 80% of project success is decided. At this stage, decisions are made about plant room locations, shaft sizes, system types. If these are wrong, you cannot fix them easily at site. By the time construction starts, changes become expensive, destructive, and contractual. Construction stage. Construction is where theory meets reality. This is the stage where value engineering happens, material substitutions are proposed, installation quality is tested. If design intent is not protected at this stage, cost cutting takes over and performance suffers. Testing and handover. Testing and commissioning is proof that the system actually works, not just on paper but in real operation. Handover ensures the building can operate effectively for the next 20-30 years. Skipping or rushing this stage often leads to operational failures, complaints, and long-term disputes. So when we talk about MEP scope, we are really talking about owning the performance of the building from concept to operation. And once you understand that, it becomes much easier to understand who is responsible for what contractually, which is what we'll look at next. Now, what is design versus contractual responsibility? As a senior level engineer, we should start thinking responsibly. Up to this point, we have talked about projects, scope, and their systems. But this is where many problems actually begin. Problems begin when technical thinking and contractual responsibility don't align. Let's start with more traditional approach. Let's talk about traditional design, bid and build projects. In traditional design, build and build projects, the consultant designs and the contractor builds. Responsibility is relatively clear. If there is a design error, it sits on the consultant side. If there is an installation or workmanship error, it sits on the contractor side. Because the roles are clearly separated, risk allocation is easier to understand and manage. Now talking about design and build projects. In design and build projects, the contractor designs and builds, the consultant defines performance, requirements, standards, and compliance criteria. This means the consultant is no longer responsible for detailed calculations and system sizing. They are responsible for defining what the system must achieve and how it is designed. This is where many engineers struggle. They continue to think and act like a traditional design consultant, even though contractually the design responsibility has shifted. Now let's talk about the critical point. In design and build projects, assumptions are dangerous, very, very dangerous. And that leads us to a very important rule. Contracts do not forgive assumptions. If something is not clearly written, if something is not clearly defined, and if something is not clearly allocated, then contractually it doesn't exist. Not in the drawings, not in the emails, not in someone's understanding. This misunderstanding of responsibility is one of the biggest reasons we see scope gaps, variations, claims, and eventually disputes. And that is exactly what we'll explore next, where scope gaps actually come from and how they turn into variations. Now let's understand where those scope gaps come from. This slide explains the root cause of most disputes we see on projects. Scope gaps don't usually come from bad intentions. They come from three very common and very human issues. Let's go through them one by one. Number 1, assumption, the biggest source of scope gap. Assumption sounds harmless, but contractually they are very, very dangerous. We often hear things like the contractor will do it, the client will handle it, the authority probably won't ask for it. These assumptions may feel reasonable at the time, but once contracts do not recognize assumptions, courts don't recognize assumptions, authorities don't care about assumptions. If something is not clearly written and allocated, it becomes nobody's responsibility until it becomes a dispute. Number 2 is gray areas. Gray areas are the classic MEP problem zones. The second source of scope gap is what we call gray areas. These are items that everyone thinks are obvious, but no one clearly writes it down. Common MEP gray areas include builder's work, power supply to MEP equipment, BMS and control integration, temporary power and water, authority fees and inspections, testing and commissioning responsibilities. Now let me give you a brief example of what is called a gray area. Now suppose for a project we have builder's work, okay? What is basically a builder's work is the provision of sleeves and openings required to run the MEP services through the civil structure elements or architectural elements. So now for an example, if we have any underground services which are passing through the tie beams and we require, and for that passing of the pipes, the drainage pipes and water supply pipes, we need to provide some sleeves and provisions that is required in the tie beam. So basically provision of pipes is under MEP scope and provision of sleeves falls under main contractor scope. Now what happens is MEP drawings only show the pipes and civil drawings only show their architecture and structural elements whose responsibility is to coordinate the services and provide sleeves and penetrations and openings, provisions, whatever is required. This provision of builder's work falls under the gray area. So if these things are not properly coordinated among the two teams, that is civil and MEP, it would lead to a gray area, which is unresolved issue, which would lead to a dispute, which would lead further to a variation. So if it is not clearly defined, it becomes a variation candidate. That is how gray areas are defined. Now let's move to the third issue, that is authority requirements. The third source of scope gap comes from the authorities. Authorities can introduce new conditions, additional equipments, design changes, different interpretation of same code. These requirements can appear after tender, after design approval, even during the construction.
If authority-driven scope is ignored or underestimated at the tender stage, one of two things usually happens. The client pays later or a dispute begins between the parties. So when you step back and look at most disputes, they almost always trace back to one of these three issues: assumptions, gray areas, or authority requirements. And once a scope gap exists, the next step is almost inevitable: a variation. So let's now look at how scope gaps actually turn into variations in real projects. Now let's talk about variations and how are they created. Variations are one of the most sensitive topics in any project. The first thing I want to clarify is this: variations are not always mistakes. They are a contractual mechanism used to deal with changes, gaps, or developments that were not fully defined at the start. Most variations are triggered by a few very common issues. Typical triggers include scope gaps, late authority comments, design development misunderstandings, poor coordination between disciplines, ambiguous or loosely written specifications. None of these are unusual. They happen on almost every project. What matters is how early they are identified and how early and clearly they are managed. A simple realistic example. Let's take a very common example: BMS integration. At tender stage, BMS integration is not clearly defined. The contractor reasonably excludes it from pricing. Later in the project, the authority or client demands full integration. A variation is raised. Now the QS reviews the variation and says this should have been included in the tender. At this point, the contractor feels it is a genuine change. The QS feels it was already implied. The consultant is caught in between. And very quickly a dispute begins. Here is the key lesson. The root cause is not BMS integration. The root cause is scope clarity failure at the beginning. How senior engineers prevent variations? Senior engineers and engineers alike don't wait for the variations to appear. They reduce them before construction even starts. This they do by preparing clear scope matrix, issuing tender clarification where scope is ambiguous, maintaining a written assumption register, engaging with authorities early, not reactively. These steps don't eliminate all variations, and they shouldn't. But they assure that when variations do occur, they are justified, easier to access, easier to agree, and far less likely to turn into disputes. And this naturally brings us to the next topic: when variations turns into claims and when claims turns into disputes. Now let's move to the next level of understanding, that is claim and disputes from engineers' perspective. The word claim often creates tension in projects. But let's first remove the fear. A claim is not a fight. A claim is simply a request made under the contract. In fact, claims are a normal part of construction projects. The important distinction to understand is this: a claim is a formal request for time and money under the contract. A dispute is what happens when the claim cannot be agreed or resolved. So very clearly, claim does not equal to dispute. Most disputes actually start as poorly managed claims. Why do claims turn into disputes? Disputes escalate when a few common things happen. First, the scope is very unclear, so everyone has a different interpretation. Second, records are weak or incomplete. Third, communication is mainly verbal, not written. Fourth, engineers panic under pressure instead of documenting facts. So at this stage, emotions take over, positions harden, and simple issues become legal problems. What senior engineers should do differently? Senior engineers don't stop claims by arguing. They stop disputes by managing information early. They do this by, number 1, issuing clear written instructions. Number 2, providing written clarifications and not assumptions. Number 3, identifying risks early, not during crisis. Fourth, maintaining proper records. drawings, emails, site instructions, test results, everything, etc. So when the facts are clear and documented properly, most claims can be assessed fairly and resolved without escalation. And this is exactly where contracts, especially FIDIC, come into play. Because contracts don't exist to create disputes, they exist to manage risk logically. So let's now look at FIDIC, simplified for engineers.
When people hear the word FIDIC, they often think of legal language and contracts written for lawyers.
In reality, FIDIC is not legal language. It is simply risk allocation logic written down.
FIDIC answers one basic question: who is responsible for what, and what happens when things change. Let's simplify the key ideas.
First, the employer defines the project scope and requirements. Second, the contractor prices the scope and the associated risks. Third, the engineer administers the contract fairly, neutrally, and based on facts. Under FIDIC, variations are normal, claims are expected, and disputes are not supposed to be the default outcome. What determines success under FIDIC is not who argues better, it is who documents better.
Simple realities every engineer should remember.
There are few very simple cause and effect rules in almost every FIDIC project. First, if the scope is unclear, the contractor will claim. Second, if the instructions are late, delay claims will appear. Third, if records are poor, disputes are usually lost, even if you are technically right. This is why arguing rarely resolves a problem. Under FIDIC, your strongest weapon is not authority or emotion. Your strongest weapon is, first, clear scope definition. Second, timely written instructions. Third, proper documentation. When facts are clear and records are complete, most issues can be resolved without escalation. And this becomes even more critical when we consider authority-driven changes, which often sits outside everyone's original assumptions. So next, let's look at how authorities influence scope and variation, especially in UAE contracts.
In UAE projects, there is one reality we must clearly accept. Very often, authority requirements define MEP scope more strongly than the contract itself. No matter how well written a contract is, if an authority asks for something, it must be complied with. This is why authority-related changes are one of the biggest source of variations in the region. Let's look at this authority by authority. Let's talk about civil defense. For fire and life safety system, civil defense has absolute authority. They may require changes related to fire pump sizing, system redundancy, detector zoning, fire stopping, and compartmentation. Even when designs comply with codes, variations often arise due to interpretation differences or update requirements during review or inspection. These changes are usually non-negotiable. Now let's talk about DEWA, SEWA, DACC, Water and Drainage Authorities. Water and drainage authorities often introduce variations related to revised water demand calculations, drainage capacities requirement, connection conditions, metering and monitoring requirements. Many of these conditions are issued at NOC stage, not during the tender. If these requirements are underestimated or ignored early, variations become inevitable and unavoidable later. Now let's talk about power authorities. Power authorities frequently trigger variations due to load upgrades, revised transformer sizing, additional backup power requirements, substation space or configuration changes. These usually occurs because actual loads turn out higher than the assumed at tender stage. Once again, compliance is mandatory. Now let's talk about the sustainable authorities, that is Al-Safat and Istidama. Sustainable authorities can introduce changes related to energy performance targets, water reuse strategies, indoor air quality requirements. Variations often occur when the compliance gaps are discovered late.
especially when sustainability requirements are treated as a checkbox instead of a design driver. What should be the senior engineer's approach? A senior engineer don't wait for authority comments to arrive. They should anticipate authority expectations before tender. They should challenge assumptions before IFC. They should clarify compliance strategy before execution. Because once authority requirements arrive on site, the discussion is no longer about whether to comply or not to comply, only about who pays and how it is managed contractually. And this brings us to the final mindset shift: how senior engineers and engineers think differently to avoid problems altogether. At this point, the difference between a junior approach and a senior approach becomes very clear. Junior engineer focuses mainly on doing the tasks right. Senior engineers focuses on making sure the right tasks exist in first place. Senior engineers don't just think in terms of drawings or calculations. They think in terms of risks. They define scope clearly instead of assuming. They write scope matrices instead of relying on memory. They anticipate authority demands instead of reacting to the comments. They protect the client's interests, not just compliances. And just as importantly, they protect their own professional license and responsibility. Senior engineers understand once a problem reaches site, the cost is already high, financially and professionally. So they don't fight problems at the end of the project. They design clarity at the beginning. And that clarity is what separates stressful projects from successful ones, and average engineers from trusted professionals. With that mindset in place, let's close this CPD session with a final few takeaways.